Yeah, you should report that information, summarize it in as short a sentence or non-sentence as possible. Okay? So an example that I might come up with off the top of my head. Determination of water hardness, which I would put first instead of the complexometric. Why would I put water hardness first? That's the goal of the experiment. So we should organize that title as much or as close as possible to why we're doing these things. Get to the point as fast as possible, unlike me talking. Okay? So determination of water hardness through calcium ion concentration complexing with EDTA. Okay? Or complexing titration with EDTA. Okay? Does that kind of make sense? So pretty much a good approach to titles is come up with all the really important words. Okay? Calcium, water hardness, titration, complexometric, EDTA, and then just jam them all into one little space and add some ats and does, and you should be okay. Okay? Like I said, I'll provide lots of feedback on that. As long as I'm seeing a solid attempt at it, you'll get most of the points. You'll just get lots of comments along the way. Okay? So this is what we're trying to do is address how you would write up the report, by the way. Okay? So what you're required to do for this lab report is you got your title, then your introduction, and then the results and calculations. So I tried to format these slides to kind of approach that. Your introduction is ultimately going to cover 3 main topics, which I guess I should have included that third one on there, but we'll see that one in a second. We want to address a why. Why are we doing this experiment? Okay? We want to address a how. How is this experiment done? And then the last thing, which we'll see in a little bit, is limitations. Okay? Are there any experimental conditions that we have to watch out for, that we have to account for when we run our experiment? Okay? So in the why do we do this experiment? Any ideas? That ultimately is our goal in this, but why do we care about the concentration of calcium ion? Water hardness. Okay? So that's our biggest why in this case, is that water hardness, or hard water, is bad. So we want some way to monitor hard water. Okay? So that's kind of our goal, our why. Okay? So what is hard water? Okay, we can address the idea that yes, water hardness is bad, but then what is it? Okay, why do we necessarily care about it? And then taking a step further, when we look at water hardness, when you define it, or the way the procedure defines it, what metal ions contribute to water hardness? Calcium's one. Are there any others? Magnesium, iron. Pretty much any metal contributes to hard water. Okay? So when we tackle this experiment, one of the things we want to do is evaluate and say, yes, these are all the things that contribute to hard water. Do we want to evaluate every single one of those? Okay? Or are we going to evaluate every single one of those? No. Why not? So a lot of that is the prep. Okay? So that's kind of irrelevant. You're supposed to add into kind of why we would only evaluate the calcium. Okay, when you go through and tackle a problem, do you go at it straight ahead with a big complex problem, or do you kind of whittle away at the edges until you get it narrowed down into an easier problem? You usually go through the easier path instead of the hardest path. That's one of the aspects of why we're only going to focus at calcium. Okay, first off, calcium contributes the most to our water hardness. Okay? But it's also easier to evaluate just that and not the other metal ions. Okay? So what we're trying to do is chip away at one aspect of it being hard water and try and come up with something that somebody else can then add to and make more complex. Okay? So it's kind of the idea on science. We come up with a big hard problem, and then we solve whatever piece we can and hope somebody else can solve the other aspects. Okay? So how are we going to go about doing this? okay, which I think is what we started with, or not quite what we started with. We're going to look at complexometric titration. So one of the things we want to evaluate there first would be complexometric. Okay, what is that referring to? Referring ultimately to a process known as chelation, okay, or a chelator. So what's happening in this particular example is that this metal ion is coordinating to these ammonia molecules. So what we have here is not really a full bond, but coordination bonds. Okay, well, why is this occurring? Okay, this is something we'll sort of address throughout the semester in lecture, and you see a lot in organic chemistry. Okay. Anything in here look particularly unstable to you? Okay, copper, I like that. Why? Why'd you pick copper being unstable? It's got a charge. Why is charge bad? It would actually be missing 2. Okay, so everybody kind of go, well, I don't understand why charge is bad. Okay, where's a good source of charge? Where have you seen charge before? See the little white boxes around the room? What do those little white boxes have in them? They have electricity. What is electricity? Sure. It's a flow of electrons, ultimately a charge. Okay, is that charge bad? No, it powers all our stuff. That's not bad. How about you stick your finger in it? Is that a particularly good thing? No. Okay, it's extremely high energy. It's extremely reactive, if you will. Charge is inherently a bad thing, a higher energy state. What we're going to try and do is always try to neutralize that charge, which is why when we plug in an empty battery into the electrical outlet, the charge flows in and starts to transfer that energy to a lower state, okay, until that state becomes really high energy, and we can now transfer that battery to somewhere else. Okay? So when we look at this, somehow or another, copper ion needs to get stabilized. What can stabilize a +2 charge? Something negative, or electrons. Okay? So we've seen, or we're seeing here, 4 coordination bonds to that copper ion. What is that coordination ultimately showing? Kind of balance of what? How is it balancing charge? Each of these nitrogens is sharing electrons with that +2 charge. How can nitrogen share electrons? 151, Lewis structures. We draw out a Lewis structure for ammonia. What do we get? A lone pair of electrons. What could that lone pair potentially do? Share with something positive. Each of these nitrogen atoms is loosely sharing its electrons with that copper ion. Okay? So this nitrogen is a partial negative charge due to those electrons, and now weakly coordinates the positive, and it does 2 things. One, it makes the positive copper more neutral, and it also makes the nitrogen more neutral. That neutral state is lower in energy, everything becomes happy. Okay? So that's what happens when we dissolve copper ion, say in an ammonia solution, which is what they end up showing. So what we get is that coordination bond. What's happening when we look at a chelator? Okay? So what we're going to do is now bring in EDTA. Instead of ammonia or NH3, we're going to bring in this extra species. Was it ethylene diamine tetraacetic acid? Something like that? Okay. And we've got the structure down here. Okay. We're going to try and bring it in near, instead of a copper ion, we're going to bring it near a calcium ion. Okay, what charge is a calcium ion? +2, so it's charged. Okay, that calcium ion now wants to become neutral. So what is it going to want to do? It needs to get electrons from somewhere. Where do we have electrons? Yeah, I heard it. From the nitrogens, which are now shown in green. Okay, why is this species different than if we added 2 NH3s? How is EDTA better than ammonia. For us to get that coordination bond, what has to happen? So we got calcium ion and we got our nitrogen. How do we get the coordination bond? They have to get close enough to each other to actually interact and form that bond. Okay? In the case of forming that ammonia complex, how many different molecules need to collide? Well, we can't have one collision, one molecule collide. We'd have to have at least two. Okay? So we could have one, there's one ammonia complexing. We could have another ammonia complex. So we've got three so far. If we remember from our copper ion, which is going to act similar to the calcium, we had 4 ammonias around it, which means we need a total of 5 pseudomolecules to interact. Okay? If we think back to rate laws, how many molecules could we get to interact pretty much at once? Okay, up to 3, and 3 was pushing our limits. 2 was really all we could get. What's the likelihood I'm going to be able to get all of those interactions to all occur perfectly? Not so great. Why is EDTA different? When EDTA coordinates with that nitrogen, where's the other nitrogen? Really far or really close? It's really close. It's only connected by 4 atoms. Okay? So as far as bond distances go, that is ridiculously close. In a solution, remember, we're effectively saying it's a gas. All of those molecules are all over the place. As soon as we link 2 chelating ligands, okay, or 2 atoms to the same structure, we drastically improve their ability to coordinate to that ion. Okay, so EDTA is special because it has those 2 nitrogens in one spot. Okay? This can be taken a step further. So let's test you on some organic chemistry material. Anybody know what that functional group is called? Carboxylic acid. Based on your definitions from 151, which I think you guys have seen, what do acids do? Donate hydrogen ions, or H+. So if we pull off that hydrogen as H+, what charge does the oxygen become? Has to become negative. So what we've got scattered around the rest of the molecule of EDTA is a crap ton of electron density. Okay? That negative charge is stable or unstable? Unstable. How do we stabilize it? Positive charge. Do I have a positive charge floating around that's potentially already coordinated to the nitrogens? Yes. That calcium ion's in there. So what ends up happening in the case of EDTA is it actually wraps around the calcium ion. Okay? And we have 1, 2, 3, 4, 5, 6 different points of contact, where if one of those coordination bonds, because they are very weak, breaks, there's 5 more to replace it. So that complex ends up becoming very, very tight, and what we end up getting is this kind of overall reaction. Okay? So we know EDTA is important. It looks at complexing, okay? And we even can get a balanced equation out of it. The one extra thing we're going to add is titration. What is titration going to do for us? Okay, if I want to determine the calcium concentration, okay, or the metal ion concentration, if I take 1 molecule of EDTA, I can complex 1 molecule of the metal. Okay? So if I know the amount of EDTA in solution, I can also determine the amount of metal in solution, which is ultimately the goal. I wanted to know the concentration of the metal. Okay? So the balanced equation allows me to determine that concentration. So that's kind of neat. Okay? So we now have kind of an overall interpretation. We've got the complex here. This is now EDTA shown wrapped around the calcium. You should see each of those dashed lines. And I copied this from the procedure, so it's not like it's a new picture. Okay? Showing that coordination. Okay? Does that make sense? So we've got an idea of how this reaction is going to work. We can slowly add the EDTA until it complexes completely with the metal. Okay? So are there any complications with this? And I'm pretty sure I didn't actually add it on this. How do we add the EDTA? Okay, well, to get EDTA to react with that metal ion, I just need to add it. So to measure EDTA, it's a nice solid. We can use the balance. We can measure out a grain of EDTA, add it to the solution. Did it complex all the way? Yep, okay, we need to add more. So what do? Measure out another grain of EDTA and you add it to the solution. Still need more? Add another one. What do you now have to do? We aren't even there yet. To get all that EDTA to complex with the metal, we'd have to weigh out each grain of EDTA. And we continue to add each of those grains up until we get all of it reacted. Okay? That's a lot of stuff to do. Okay? Each grain weighs fractions of grams. So you'd have a little weigh paper, you put a grain on it, add a grain. Grain, grain. It's going to take a very long time just to one reaction. Okay, so what do we do instead? Instead of adding it as a solid, we want to add it in a liquid. Okay? To make it a liquid, we'd have to melt it. Melting point is ridiculously high, so I heard a better suggestion in the back. We'll dissolve it in a solvent. So we'll dissolve it in water. Okay? So now what we can do is add a set bulk amount of EDTA to a water solution, okay, which in theory doesn't have any calcium ions in it. Okay? Get that all dissolved and then slowly add that solution across. However, we need to know exactly how much EDTA is in that whole solution. Okay? If we make a small mistake on the balance, it turns into a large error in our final result. So the very first thing we have to do, determine the concentration of EDTA. How do we do that? Molarity. What we're going to do is a standardization procedure. So we will titrate that EDTA solution with our calcium ion, with a known calcium ion concentration. That way we can back calculate what the molarity has to be, and we can get a much more accurate representation of our sig figs. Okay, so we can get a better answer at the end. Okay, so that's one of our complications to this. What's the other complication? What color is EDTA? Clear. What color is calcium ion? Clear. What color is an EDTA calcium ion complex? Clear. How do we know when all the EDTA has reacted, or all the calcium ion has reacted with all the EDTA? We don't. Okay, so that's a pretty big complication. So what do we come up with instead? We're going to have to add some kind of indicator that allows us to monitor one of those. Either the complex product at the end or the metal ion in between. Okay? Between those two choices, which ones do you think is easier? Do we want our indicator to react with an EDTA calcium ion complex or with just a calcium ion? Probably just the calcium ion. It's smaller. Okay? It already hasn't done all the interactions it can. Okay? So it makes sense to have our indicator react with the metal ion. That's where aerochrome black tea comes into play. Okay? So what we could go through and do is see how it responds. It does happen to react with the metal. The indicator in its free state without any metal is blue. When it reacts with metal, it becomes pink. Okay? So if we now push this to our reaction, in our initial state, we'll put our indicator in our solution with our calcium ion first, which means we get the complex, we get the pink color. Okay? As we add EDTA, what ends up happening? EDTA starts to react with the metal and remove it from the solution. As long as there's still metal present, we'll still see that pink color, until eventually what happens? EDTA strips the metal ion away. Now the indicator doesn't have any metal, and it changes color to blue. Okay? At that point, I now know that the EDTA and calcium ion concentrations are equal, or moles are equal. Okay? I can use that information to determine the molarity of the EDTA for my standardization. Okay? I can also use that once I've got standardized to then go through and determine an unknown calcium ion concentration. Okay? Make sense? Questions about that? Okay, a couple of other things I want to address with this. We are going from pink to blue. I think I want to address it now. Aerochrome black tea is a little bit slow, so when you think you're getting close to that transition, slow your addition down substantially and give it a few seconds to actually swirl. It might actually convert across to the blue color, okay, without having to add more. So you want to be as careful and slow with this as possible, within reason. We do only have 2 hours to do it. Okay? Yes?
What happens if you add too much?
If you add too much, it sounds like the volume of EDTA necessary is more, which means that your calcium ion concentration appears to be more than it actually is as well. So you end up with an inaccurate result. Okay? How do you know you've added too much? Good question, you don't. Okay? So how can we account for that error? An individual attempt could be wrong. What happens if you do it a second time? It could be wrong again, but in theory what you can do is start to average out that human error. Okay? So that's why when you do these experiments, and you'll do it for the rest of the semester, you'll repeat each experiment multiple times. Okay? So when you do your standardization, you're going to have at least 3 trials. When you do your calculation or your determination of the calcium ion, at least 3 trials. If you think one of those trials is way wrong, what should you do? Do it a 4th time. Okay? If you already have the impression that your experiment is wrong, you can fix that mistake now. If you wait till you get out of lab, run the calculations, what ends up happening? Your result's wrong, which means ultimately you lose some points. Okay? I'm not grading strictly on your results, but that is a part of your grade. Okay? So try and be as accurate as possible, and you shouldn't have to worry about that. Okay? Other questions on that? Yes?
So we're looking for right when it starts turning blue?
Right when it pushes to blue, yeah. Other questions? Okay. Is there anything else that's kind of important to note here? So far we've mentioned EDTA, aerochrome black, and calcium ion. Is that all we add in the reaction? No, we add ammonium. Why do we add ammonium? If we look at our overall reaction, is it only EDTA, metal, and indicator? No. H plus is also in this reaction, which means H plus can control whether this reaction works or not. So what we need to do is make sure that the H plus concentration stays relatively constant. If it changes too much, it can change the appearance of our color. Okay? So to stabilize our pH, or stabilize the H plus concentration as much as possible, that's why we add the ammonia. Okay? Necessary to make sure that we get accurate results. Okay? Other questions? Okay. Is there anything else? Are there any interesting units that we should mention? Probably. Good answer. Okay. The unit that we use for calcium carbonate is not molarity. What do we use? We use milligrams per liter, okay, which I don't think gets a special name, because molality is kilogram per liter, gram per liter. It's kilograms. So we don't really have a special name to give it. So it's important to mention that. When we measure water hardness, we're measuring it with a different set of units. We're looking at milligrams per liter. Were there any other units that were shown up? Kind of. We'll talk about that in a second too, but it's not our water hardness officially. Parts per million. Okay. which is the same number. You don't have to do any conversions. Your milligrams per liter is officially parts per million. Okay? So we get 2 new-ish units that are getting mentioned. Okay? The parts per thousand is important to evaluate in our standardization. When we standardize the EDTA, we're trying to get its concentration. Okay? And we ran a whole bunch of experiments, and we could average all those results to get a molarity. But what if those molarity values were all drastically different? Does that allow you to trust your molarity result? No. If you can't trust your concentration of EDTA, can you trust the water hardness result? No. So we need to come up with some way that we can report that trust value. That's where we come up with PPT, or parts per thousand. That's your precision in your EDTA calculation. In theory, that should be no bigger than 5 when you do that calculation. Okay? It is fairly straightforwardly explained as far as how to calculate that in the procedure. Okay? Just in case you go through and calculate it and you get anywhere from 10 to 50, okay, what does that mean? Didn't do a very good job titrating. That's about it. Okay? Don't panic. It's not a bad idea to check your work just to make sure you did the math right. But it just means you didn't do as accurate a job as you could have. Okay? Again, that contributes to your grade, but it's not that big of a deal. Okay? Your parts per thousand will probably get graded at most 5 points out of 50, probably looking more at 2 or 3. Okay? So if you happen to hit it right on, I'll give you full credit and maybe even a few bonus points. And then if you're anywhere under that, or technically over that parts per thousand number, kind of lose points from that total. Kind of make sense? Okay. We kind of already addressed this. If we had other metals present, that does ruin the experiment. So when we test, we make sure that our unknown sample only has calcium ion. Okay. Any questions about anything else that we just discussed? Okay. The experiment itself. Ammonia is toxic. Please be careful with it. Its toxicity level is like 1,000 times above what you can detect. Okay. How do you detect ammonia? Smell it. If you can smell it 1,000 times greater than that, it's toxic. Okay. So please be careful with it. Work with it neatly in the hood, which brings up an issue with the hoods. The hoods should be at a particular setting. Anything higher than that, or technically lower than that, they stop working appropriately. When working in the hood, the sash or that pull-down thing should be at the level marked on the left or right. I don't remember which side it's on. Okay? That is going to be particularly important for anybody working at the extremes of the lab, because that's where the hoods are. Okay? So for those of you working there, sorry, it's going to be yelling at you all these next 8 weeks. Okay? So you might let students know politely, hey, can you pull that sash down when you're done with it? That kind of thing. In your standardization procedure, if you exceed over 35 milliliters, something is wrong. Okay? Before you get to that blue color. I still do not understand why it's not working, but for some reason, some students just don't get the official full blue color coming out of it. Okay? According to my rough calculations, if you did everything correct in making your EDTA solution, you should need roughly 25 milliliters. Okay? So that 35 milliliter mark is in case you measured something slightly differently. Okay? So yeah, if you don't get that blue, then just restart that trial. Okay? If it happens again, or if it happens once, you might talk with me, and I can take a look at it and see what's going on and ask what you did, and maybe even watch you while you set up the next trial to make sure you're not missing something. Okay? Like I said, I have no explanation for why it doesn't fully change. It just, for some reason, doesn't seem to do so. Roughly 10% of the trials. Okay? As far as the calculations go, you're going to have to standardize your EDTA molarity, so that's part of your procedure. And then you've got an error calculation, and that's your precision, the PPT value. Okay, we'll walk through some of that calculation in just a second. The last calculation you'll do is the determination of the water hardness, which is ultimately the reverse of the EDTA calculation. Okay. As far as your results sections go, okay, I do not need to see all your initial final burette readings. Okay, that's just going to be excessive. So what I've done is summarized it into ultimately 2 tables. Okay, the table on the left represents. Okay, so in a report you would say table 1, and then you'd come up with a nice little description of this, but I'll come up with a terrible one to start off with. Okay, your standardization, okay, of EDTA. You'll notice I've included units in the table. That way, I don't have to include units for every single entry. Okay. The second table is going to be your determination for water hardness. Okay. What things are coming from your experiment? What entries in these tables come from the experiment? Only the volume of EDTA. The molarity and the water hardness are calculations. Okay. This format will at least keep it nice and neat and easy for me to interpret. You do not have to maintain this format for the tables, but I would highly recommend something along these lines. Okay? Calculations. Do you want me to go through the calculations? So we'll go through part of the calculations. We'll look at the EDTA. So first thing that we'll need for all of these would be a balanced equation, which we'll do just roughly EDTA and metal. We change that metal to calcium. Is there a question there? Our EDTA calcium complex. Okay. So in our standardization, I guess I should have put this at the top. Okay, what information do we know? We know the volume of EDTA added. We do know the mass technically. However, the mass is something that we're only using to make our solution. We don't need it to determine the molarity. That's why we're doing these standardization trials against calcium ion of a known concentration. Okay. So the mass of EDTA does not need to show up in your report. As far as an observation goes for the lab, it's something I would expect to see in the lab notebook, mainly because that's one way I've checked to verify that students mess something up. Okay? So you should note that just to make sure, but that does not need to show up in any calculation.
What does it represent?
The mass of EDTA that you weigh out. What else do we know in this reaction? We know the molar or the concentration of our calcium ion, which should be written on the bottle. Remember, this is our standardization. We're using a known concentration of magnesium or calcium ion, milligrams per 1 liter. What else do we know about the calcium ion? What's that? Yes, and we will need that in a little bit. So we know the molecular weight for our calcium ion, or sorry, for calcium carbonate. Why do we have to do calcium carbonate? When they make up the calcium solution, do they just add calcium ions? No. Why do they not just add calcium ions? You can't get calcium ions by themselves. Why not? They're charged. Okay? We need something to stabilize them. In this case, our standard state is calcium carbonate. Carbonate works very well to coordinate with the calcium, generates a nice stable solid that we can measure out. Okay? What else do we know about the calcium solution? You'll know the volume of the calcium ion solution that you start with. Okay? How are you going to know that volume? You measure it. So that's a nice, easy way to figure out that you've got it. Okay? So what we ultimately want to figure out is the molarity of our EDTA solution. Okay? And more volume. This is going to come from the burette. So we'll call this BV for burette volume. Okay? So, to calculate the molarity of EDTA, what is molarity? Moles per liter. So if I want to figure out the molarity of EDTA, I need to know the moles of EDTA, and I need to know the liters of EDTA. Do we know any of those values right away? We know the liters or milliliters. Okay? We do have a volume. Okay? We've got our burette volume in theory in milliliters, so we could convert that over into liters. Okay? Do we know the mole value? No. Is there a way we could figure out the mole value? Did you say math? Yes, math. Okay. We've got a balanced equation. So let's say I start with 1 molecule of calcium ion. How many molecules of EDTA are necessary? 1. What if I have 1 mole of calcium ion? 1 mole of EDTA. How many moles of calcium ion did we start with? Can we determine that? Yes. So what we can go through and do is take all of our starting information of calcium ion and try and determine convert that into moles of EDTA. So the first thing I would start off with is that we have 10.00 milliliters of our calcium ion solution. Okay. Do I have any conversion factor that can allow me to convert the milliliters to anything else? Why do you want to go into liters? I can accept that. We do want liters eventually, so we could include that. Can I convert the the liters now to anything else? What could I convert it to? Kind of. Milligrams using the concentration. Okay, I have 1.000 milligrams in 1 liter. Now I've got milligrams of, I know this is definitely a bit misleading because of how I'm abbreviating it. Is it calcium? It's calcium carbonate. Remember how they made the solution. Okay. Remember, I'm trying to ultimately get into mole unit. Can I convert milligrams to moles directly? No, but we do have another relationship, grams to moles. So I can convert milligrams into grams. 1,000 milligrams is a gram of calcium carbonate. Can I convert grams into moles? Yes. How do I do that? 100 grams of calcium carbonate per 1 mole, technically of calcium carbonate. What can I do now? Can use the balanced equation, technically, I would actually say we're going to do another thing in here, and since I'm going to run out of space to jam it in here, maybe I'll fit it. Can't use the balanced equation quite yet, because does our balanced equation show carbonate? No. So what we need to do is convert moles of calcium carbonate into moles of calcium. How do we do that? It's 1 to 1. How do we know it's 1 to 1? Not the balanced equation. From the balanced formula, it's a 1 to 1 relationship. Okay. Can I convert calcium ion into EDTA? Yes, from the balanced equation, it's a 1 to 1 relationship. Okay. I now know the moles of EDTA after that big long calculation. I know it's a bit crammed there at the end. Okay? Kind of makes sense? Now that we know the moles of EDTA, I can then divide by the burette volume that I added, and I now have the molarity for trial number 1. What do we do? Repeat it for trial number 2. Repeat it for trial number 3. Then what do we do? Average it. Now we know the concentration of EDTA. We can now use that information for our unknown. And we'll tweak this a little bit to kind of address that, but I'm not going to go through all the calculations. Okay? The last thing that you would do is do the percent, or the parts per thousand, which is your precision value. To do that, you'll take each trial minus your average. You'll average those values for each trial and then divide by your average. Okay, I know that's something really repetitive, but it's actually explained fairly well in the lab procedure. Okay. Questions about the standardization?
Well, is that each trial minus the average of the trial?
Each trial minus the averages. Average that difference. Divide by the average molarity. So there's lots of averages. I know. Okay. Each trial minus the average molarity is the absolute deviation. You take the average of the absolute deviations, divide by your average molarity. Calculations that I've seen so far have come out 10 to 20 as your number. It's a lot easier to do once you've got numbers. Without numbers, it becomes a bit difficult to explain. At this point, you'd then move on and do your unknown calcium ion calculations. To do that, what ends up changing? So now it's no longer our standardization, but now what we've got is our water hardness. If we go back to that initial information, what information do we not know now? We don't know our milligrams per liter for the calcium ion. We will know the molarity of the EDTA. Okay. We'll end up doing pretty close to the exact same calculations, just in reverse. So take everything and flip it over. Your lab handout sheet does tell you how to do that calculation. For the discerning eye, you'll notice that their units don't make any sense. Okay? And the reason their units don't make any sense is because they decided to remove a conversion factor. Okay? Or in fact, 2 conversion factors that cancel each other out. Okay? So that's why they didn't worry about it.
So do you want us to follow that one that they have?
It's fine if you follow that, yeah. Yeah, it's not going to hurt one way or the other. Any other questions with it? Okay, so to go ahead and get started, what